Everyone. I am Tabassum Shifa and today I am presenting my final assignment course for the Digital Logic Circuits titled Digital Parking Control System. This project combines digital logic, counters, timers, FSM and HD on-off. The goal of the system is to monitor the number of cars in a parking garage and display the status using 7 segment displays. We have in total 12 cars. If the garage is full, it will show full continuously, and if the space available, it shows space available in blinking manner. Sensors placed at entry and exit gates to count cars coming in and out. Here is the question. In first question, we have to show the block diagram. This is the block diagram of the system. This The main components include entry and exit sensors to detect car movement, a JK flip-flop, up-down counter to keep track of how many cars are inside, the comparator to check if the count has reached the maximum capacity, to display driver, one shows full and another shows space available through 555 timer. There is the flowchart. The system starts and takes input for maximum capacity from the keyboard, entry and exit sensors to detect the cars, the counter is updated, either is incremented and decremented. Then the count is to compare with the maximum capacity. If the counter count and the maximum capacity is equal, then it will display full. If it is not equal, then it will activate blinking space available display. Then we have JK flip-flop counter. Each flip-flop toggles when JK and K are set 1. This allows counter to count from 0 to 15, which is more than our 12 car capacity. The entry sensor sends an up signal and the exit sensor sends down signal, which we shows either 1 and 0. Here is the 4-bit counter diagram. Then we have in question 2, triple five timer. In the first triple five timer, it will show full, which is it's a monostable mode. In the monostable mode, we know it is useful for one-time notification. On the card entry, exit, it will stay in one mode. Then we have triple five two design. It will show space available in a blinking manner. It will be in a stable mode. For stable mode, in no internal trigger needed, it runs automatically. In the question, we see there is a P and there is a D duty cycle, which is 48%. Then there is F frequency, which is 8 Hz, and there is T 1 by F. So we get 0.125 second. Then for, as we know, D is equal to TH by T. From that, we figure out T, which is 0.06 second. Then in TL, which is 0.065 second, we took capacitor is 250 microfarad for better calculation. Then we figured R2 and R1, which is 375.18 ohm and R1 is 28.25 ohm. There is the diagram we see, and this is the control logic. In the third question, we see FSM. To control the further blinking output, I designed finite state machine. It has two states, which is SO, where A is on, B is 0, and S1 for A is 0, B is 1 for 4 milliseconds. Since the clock period is 1 millisecond, the FSM holds each state for 4 cycles before switching. Here is the state chart diagram. If you see, for each state, it changes one by one, and it shows A, the output by A, and for next 4, it should B. If we convert it into the binary code, if we see the state table, for every uh, 4 millicycle for every 4 cycle from 0 to 3 there is a will be all 4 and b will be 0. From 4 to 7 a will be 0, b will be 1. There is the aerial code which is showing this code uses 3-bit counter to track counter cycles and state variable to toggle between 1 and 2. Here is the input is where clock and input is resist. Output where will be one A and B, and then there will be two state, which will be present state and next state. This code ensures the output A and B alternate every 4 milliseconds, creating a clear blinking effect. Here is the FSM diagram. And the last one is limitation and improvement impact. Some limitations are it can only handle 12 cards due to 4-bit counter. If if the if they have more than 12 counter, it won't work. Triple five timer doesn't have an enable pane, so extra logic is needed to run for on and off. Also, sometimes sends a glitch for the fast movement. It may cause counter issues, and it doesn't store any data, which also can lead to security purpose which also can lead to security purpose. And there's improvement. We can use wide counter for like 10-bit counters. It can store 1023 cards. We can replace triple five timer to microcontroller. Instead of keypad, we can use central system. And the impact will be all of this. For adding more bit counter, it will increase more complexity. It will if we change into microcontroller, it will make better power facilities. Adding another sensor, the central system will cost up very effectively. But to summarize all this, it will be better if we improve the sparking system. The system shows how digital logic can solve real life problems. Thank you for watching.